Here's a start and stop example for conservation of energy. We have a 10 kilogram block that's released from point A of a track as shown. The track is frictionless except for the rough region between point C and D, which has a length of 6 meters. At point E, the block hits a spring with spring constant K equals 2,150 newtons per meter, compressing at 0.350 meters to point F before stopping for a moment. I want to know what the coefficient of friction is between the block and that rough region of patch between points C and D. So first off, I'm going to start with trying to figure out what the block's initial energy is. That's the block's energy at point A. So that's going to be determined by gravitational potential energy. When we sum up all of the energy contributions, we see that gravitational potential energy is the only thing that's really got a value. Our kinetic energy so far is 0, and we haven't compressed the spring yet, so there's no potential from spring compression. So when I calculate the gravitational potential energy, I get 10 kilograms times 9.8 times 3 meters, because it's 3 meters off the ground, for a total of 294 joules. This will be the amount of energy that we start off in the system. It's the maximum energy that our block's going to have. Everything after this is going to get lost. Let's figure out what our block's energy is at point B. Well, it should be the same as it was at point A, so we'll just set it equal to A because we're not losing anything to friction yet. So it's just 294 joules. What's the block's speed at point B? Well, that's going to be derived from our kinetic energy. So our kinetic energy equation is 1/2 mass times velocity squared. We know what the kinetic energy is, so we're going to rearrange the equation and solve for V as root 2K over m. When we actually put the numbers in, we get 2 times 294 joules over 10 kilograms, square root. And it turns out that our speed is going to be 7.67 meters per second. That's how fast the block is going as it slides toward that rough patch. Let's find out what the block's energy is at point C. Now this is at the beginning of the rough patch, and we haven't hit any rough patch up until point C, so there's no reason for us to believe that the energy is anything other than what it was at point B. So it's just 294 joules. Now we're going to play it backwards. Let's find out what the block's energy is at point F. That's at the end where it has compressed the spring a distance of 0.35 meters. Now it takes a certain amount of energy to compress this particular spring 0.35 meters. So let's find out how much energy it had to do that. Well, that's going to be the same amount of energy as is now currently stored in the spring. So when we add up all of our energy components, that's the only energy component that we're interested in. And so we see that that's 1/2 times our spring constant of 2,150 newtons per meter times the distance compressed squared, which is 0.35 squared. And we're going to end up with 132 joules, which means our spring is now storing 132 joules. That's all the energy the block gave it. So the difference is going to be the energy that the block lost on that rough patch. So when we play that backwards again and we say, well, what's our energy at point E? Well, that's going to be the block's energy that was devoted to the spring, so it's going to be the same as it was at F, except now the spring energy is 0, all that energy is in the block. At point D, there's no reason that the energy at point D should be anything other than what it was at point E, so we'll just set that equal to 132 joules. Now we're getting to the crucial part. We know what the energy was at point C, and we know what the energy was at point D. Anything in between is the amount of energy that was lost to friction. So how much energy does the block lose to friction between points C and D? Well, that's the difference between what it had at point C and what it had at point D. So the difference is 162 joules. So that's the amount of energy lost to friction as the block slid over that 6 meters of rough patch. So what was the force of friction between points C and D? Well, what force of friction caused it to lose that 162 joules of energy, that did the work of 162 joules? Well, remember that work is force times distance, so that frictional force that was doing the work must be equal to that work divided by the distance. We know the distance, we know how much work was done, and so the total amount of force over that entire patch of rough area there must have been 27 newtons. Finally, we're getting down to what we were after. We want to know what the coefficient of kinetic friction is between the block and that rough region of track between points C and D. So we know what the force of friction is. How much coefficient of friction do you need for this particular block in order to provide that amount of force? Well, our coefficient is just the ratio between the frictional force and the normal force, which is the weight of the block. So I know that it's just F sub F divided by mg. I know what all those values are, so I can plug them all in. So I have the force of friction is 27 newtons divided by the product of 10 grams and 9.8 meters per second squared, which gives me a coefficient of 0.276 between in that region between C and D. So that's what my coefficient of friction was, and that's effectively the whole problem.